All right. Welcome everyone to Astronomy on Tap, the Los Angeles chapter. This is our June event. I think it's June, right? And we've got a great event planned for tonight. I'm Dr. Cameron Hummels, and I'll be one of your MCs for the evening. And the other MC is Dr. Kaylin Henderson, drinking whiskey, I think. You're
Yeah,
muted.
a month ago, I went with a peatier scotch. Today, I'm going with the Oban 14. Because while it's true that there are no laws when you're drinking claws, this is a very classy, family-friendly establishment.
Okay. Yeah, so and we're joined by two speakers tonight, Dr. Arya Udry, professor at UNLV in Las Vegas, and Dr. Paz Beniamini, a postdoctoral researcher also at Caltech with myself, who originally hails from Israel, right, Paz?
Yep.
Awesome. So welcome everybody, welcome. So Arya, you were saying that it's quite hot in Las Vegas right now.
It is. It was 112 today.
Oh, jeez.
Very hot. I mean, it's no surface of the sun, but that is hot for the surface of the Earth.
Yes, that is hot for the surface. And Paz, what is your background?
So this is a painting of the gamma ray belts. You can see it.
Oh, that's awesome.
So cool. That's so cool.
It's not a photograph.
Okay. Maybe we'll see some photographs during your talk.
Unfortunately, we never get that close.
Oh, yeah, I guess that's true. They're all artist conceptions. Kaylin, and obviously it's the surface of the moon. Do you know where on the surface of the moon your background comes from?
No, I'm not sure. I think it's actually a composite. I tried to trace it from what I had thought was the kind of classic Earthrise photo. But if I remember right, it's been a couple weeks, the surface of the moon actually looks different for a lot of the Apollo, is that 8 images. So I'm not actually sure.
Okay, that's cool. And I guess following up, I don't know where this is from. It's an image of a starscape with dust lanes. Wait, where are the dust lanes? There's the dust lanes.
It's from Spain.
Spain.
Yeah.
Yeah, so anyway, all right. So if this is your first time, obviously, normally we do our Astronomy on Tap events in person at a bar, but we aren't doing that tonight. And we haven't been doing that since March because of the pandemic. So we're doing these once a month. The layout for tonight will shortly, when I am done yapping, I will introduce Paz, who will speak first for about 15 minutes. Then we'll take questions. You're free to write questions in the YouTube comments on the side of the live stream throughout his talk, and we'll try and get to those for a few minutes after his presentation. And then following that, Arya will give her presentation on space rocks, because space rocks. Space rocks rock. So that should be super awesome. And then we'll take questions similarly for Arya. And then following that, we have pub trivia that we've all assembled with a couple of questions relevant to the talks that are being given, and then other questions that are just related to what's in the news in terms of space. There's a Star Wars question, because there's always a Star Wars question. And yeah, and we'll have fun with it. So if you guys have, and the pub trivia is done super interactively like it was last week. So you guys can go to a website and see how other people are responding and see how you're responding. And it's pretty fun. So
yeah, don't worry, you don't need any sort of login or user account, and there's no data being tracked. But
right,
it's kind of a format that allows us to have a little bit more interaction, even given our virtual Astro on Tap. Right. I do have one question. So I am drinking some scotch. Does anybody else have any exciting beverages, adult or otherwise?
I also have a whiskey.
Ah,
Oh.
right.
Oh, you can't actually see it.
Oh,
It seems like I'm holding
It's in front of you. I can see.
holding just an invisible glass, but it is actually there.
I have, well, I can't even see it. It's not invisible. This is a Bitburger Pilsner. It felt like a refreshing beverage. It's not 112 degrees here in Pasadena, but it is, I don't know, 86 degrees in my apartment. So I thought that it would be nice and refreshing. But this is my first beverage of the evening, so we'll see if it progresses beyond this. I'll keep you abreast if that's anyway. Oh, and Aria, you have water. See, that's the smart move.
Otherwise, my talk would be in French, which I'm not sure everyone wants that.
That could be cool. That could be very cool. All right. All right, let's all turn off our video except for Paz. Just a quick introduction. Paz is a postdoctoral researcher here at Caltech. He's originally from Israel, and he works on theoretical topics in high energy astrophysics, including gamma ray bursts, fast radio bursts, and basically other things that have the word bursts in them. And the fun fact that he has is the picture in his background is actually as he said, a painting of a gamma ray burst, but he himself painted this, which I think is super, super cool. So I will leave it to you, Paz. Thank you very much for joining us.
Yeah, thanks a lot for having me. So let me share my screen. Here we go. Okay, so hopefully my slide is visible now.
Looks great. Looks great.
Okay. So yeah, I want to tell you a bit about gamma ray bursts today, and mainly kind of talk you through the discovery and kind of try to give you a feeling of what it was like for the process, not that I was there, but for the process of the discovery, and the kind of clues that we get from these objects, and how can we start deciphering them to sort of figure out what's the underlying physics that's going on. So these are called gamma ray bursts. So of course, it's not surprising that we will first have to talk about gamma rays. So gamma rays are a type of electromagnetic wave. And electromagnetic waves are this kind of phenomena that you can see here in this figure on the top. And basically, you have this situation where there's an electric field in some direction in space. In this case, it's in the y direction. A magnetic field in some direction in space. In this case, it's the z direction. These electric and magnetic fields are going up and down as a function of time. And all of this thing is propagating in space in the direction that is perpendicular to those two. So this is a lot of words, but actually it's quite easier to understand if you just look at it in an animation. So I will click this, and you can see this whole phenomena kind of moving along the x-axis. Okay, so this is what an electromagnetic wave is. This sounds maybe a bit obscure, but actually it's a very generic thing. And it turns out that this kind of phenomena called electromagnetic waves is something that we experience all the time in our day-to-day experience, and in all sorts of forms. And the thing that differentiates different types of electromagnetic waves is the frequency of this wave, how quickly the electric field or the magnetic field are going up and down as a function of time. And you can see this here in the bottom figure. If you look, for example, at the axis that's not the most bottom one, but just one above. So this is, as a function of frequency, the types of electromagnetic waves that we have. And you see that at the low end, you have radio waves. These are the same kind of radio waves that are used for FM radio, whoever still uses FM radio, or are used for mobile phones to get your reception on the mobile phone. If you go to higher frequency, then you go into the microwave. That's the same kind of phenomenology that we have in our microwave oven. Then you continue going up in frequency, you reach infrared, eventually visible. Notice how small the visible spectrum is. You can see it's barely, like a very thin strip here in this whole spectrum. And this is all of the light that we can see with our eyes. All of the different colors are different points on this line here. And everything else basically is the same type of physical phenomena, but we can't see it with our eyes. So kind of try to imagine what it would be like if we were able to see more than just this very narrow strip. and how rich the phenomena that we would be able to see, or what a mess we will be able to see in that situation. If you go higher up in frequency, you go to ultraviolet, X-rays, and eventually all the way at the end of the spectrum, you reach gamma rays. So these are the most high frequency electromagnetic waves that we observe. They are associated with high energy phenomena. It turns out that if you look at the electromagnetic waves, you can think of them, this is an understanding that comes from quantum mechanics, as coming in packets, which physicists call photons. And the higher the frequency of the wave, the higher the energy of each individual packet. And so these highest frequency waves are also the highest energy waves, which you can see here in the bottom axis. And so the type of radiation that we see from gamma ray bursts is very high energy radiation if you look at it per photon, per packet of electromagnetic waves. So this is the range, the typical range of photons that we see. So the question is, what can make those kind of gamma rays that we see? What can make this type of electromagnetic waves? So we've already alluded to the fact that you need a lot of energy. And you can see here also in this figure, this famous symbol that signifies nuclear reactions. So this is indeed a process that requires a lot of energy, the type of energy that we have in the nucleus of atoms, and the type of energy that we get from nuclear type phenomena. So it's the same kind of thing that you can get from radioactive power plants or from nuclear bombs. So if we go now to an astrophysical point of view, one can ask, how do we observe all these different phenomena? And you see that to observe them, we build different kinds of telescopes depending on the wavelength or the frequency that we want to observe. And some of these are better to observe from Earth, some of these are better to observe from space. And you see here just a random collection of examples going all the way from radio to microwave to infrared to visible, X-rays, and eventually gamma rays. And the important thing about gamma rays in this context is that it turns out that our atmosphere is opaque to the passage of gamma rays. What this means is that if you fire a gamma ray from out of space, it doesn't actually manage to penetrate all the way through the atmosphere. And that is pretty good for us because if we were bombarded constantly with gamma rays from space, this would have some serious health negative effects on us. So from our point of view, this is pretty good. But from the point of view of astronomers who want to detect those things, that means that if you're just sitting on Earth, there's a limited amount of stuff that you can see. So it turns out that it's quite useful to send these telescopes into space, like these Fermi and Swift telescopes that you see here. And this is the way that these days we detect, for example, gamma ray bursts. Historically, the quest to look for gamma rays in space is actually something that is not that old. So it turns out that in the first half of the 20th century, astronomers had some pretty good arguments for why we shouldn't expect to see gamma rays at all coming from space. And they were not too motivated to try and look for them. It was very expensive to send a telescope into orbit just to look for something that they didn't think was there. And so this was not done. Things change actually with the element of politics. And the way that this comes about is in 1963. So the US, the USSR, and the UK signed at the time the Nuclear Test Ban Treaty. And this was basically an agreement between those nations to prohibit test detonations of nuclear weapons above ground. So in the years leading to 1963, more and more nations gained nuclear capability and started testing huge nuclear bombs, much larger even than the atomic bomb that was used in the Second World War. And they started realizing that these have some serious and long-lasting radiation effects that we would like to avoid. So there was this agreement between nations to stop testing nuclear weapons above ground. Of course, these are not nations that are extremely friendly at the time, and so they had to make sure that this actually takes place in practice. So in the same year, the US launched the Vela satellites, which were designed for sort of two purposes. First, to detect nuclear explosions in space, if there is such a thing. As I told you, they were not too concerned about this idea because they didn't think that there was a good chance to see something. And the second was to look directly downwards into the atmosphere and see if there's any signature of nuclear activity on Earth, despite the nuclear test ban treaty. So what they detected, an interesting thing that they detected they actually detected several things because they detected some flares from the sun, for instance, and other things. But a very interesting thing that they detected happened in 1967. And this was a very bright flash of gamma rays that was unlike any known nuclear weapon. And you can see here the resulting astrophysical paper that they published about this, because you already know where this talk is leading, and you see the title of the slide, you know where this is going. But notice the difference in time. The discovery was 1967. The time at which they actually published the paper is 6 years later. It's 1973. And you can ask, why is that the case? So it turns out that there are multiple answers depending on who you ask. The answer that I got when I first learned the history of gamma ray bursts was maybe the more interesting answer, but possibly not the correct answer. So that answer was that they saw these gamma rays, but it took them a really long time. They wanted to be super, super careful to make sure that this is not some kind of nuclear weapon that that had some signature that was not what they expected, and they wanted to make sure that before they make this data public, that this is really a fully space-related phenomena, nothing to do with human-made activity. And it really took them a long time to reach that confidence. It turns out that the reality is actually a bit more mundane, and in interviews with the first author on this paper about 10 years ago, he actually said that, no, we realized very quickly that these are not nothing to do with humans, and even it was clear from the direction, they could exclude the direction of the Earth from early on from their observations. And simply the reason that they didn't publish it was because they thought it was not that interesting. So it turns out that this was the reason why they waited. They thought, I don't know what these things are, some weird bursts from space. Let's just leave it in a drawer somewhere and maybe later we'll do something about it. This is the first event that they saw. So what it looks like in a gamma ray detector, you count how many gamma rays hit your detector as a function of time. And you see here the amount of counts that they got as a function of time. You see that there's kind of a complex structure. It's going up and down, and then going up and down again. You also see that this thing lasts several seconds. And this was it. Over time, more and more gamma ray telescopes were sent to space, and with better capabilities. And you can see here that during the decades, our ability to discover gamma ray bursts has really increased significantly, where these days we can detect basically one per day, more or less. All these detections, you want to use them in order to actually understand something about the physics. So what are the pieces of information that we have? One piece of information is looking at those light curves, the same as the one that I showed you from the first GRB. GRB is just an acronym for gamma ray burst, in case I haven't actually spelled it out. And you see here the kind of more modern data, and you see that it's very messy. You see some GRBs that have one pulse, some that have several pulses, some have this very sharp rise and then a very slow decay. It seems very chaotic and all over the place. So there is this kind of saying in the GRB world where when you see one GRB, you see one GRB. And it's very difficult to conclude based on this really what's going on. There's a limited amount of information that we can gain from these light curves, at least at first glance. Another thing that one can look at is the spatial distribution of gamma ray bursts. And what this is imagine that you take all the directions in the sky and you put them on this map that you see here. And the direction that is right towards the center is the direction of the center of our galaxy. And then these coordinates are longitude and latitude relative to the frame of the galaxy. So if you were to draw the galaxy in this kind of picture, it would just be some kind of horizontal line here across the center. And so you can ask what would be the spatial distribution of gamma ray bursts. Each time I see a gamma ray burst, I pinpoint its direction relative to this frame of reference, and I mark it down, and I see what the eventual distribution is that I get. And this is what they got with different telescopes. And you see that in both cases, it seems to be pretty much all over the place and uniformly all over the place. So it turns out that this actually tells us something quite interesting. But before I tell you exactly what it tells us, I want to show you one more thing, which will be important, which is that these gamma ray bursts, when they happen, they are extremely bright. So what you see here is, again, this map of gamma rays, and this is the background gamma rays before any gamma ray burst has happened. So you see that there's always some background level of gamma rays. This is coming from all sorts of sources in the galaxy. So here, white is the brightest, it's the most amount of gamma rays, and blue is the faintest. So you see that there's this strip going along the galactic plane as expected, because all of these sources are in the galaxy, most of them are in the galaxy. And what I will show you now in this short animation is how this gamma ray map looks when the GRB is taking place. So I will play it first, and then we will talk about it. So you see that the GRB has happened somewhere to the north of the galaxy. And during the moment of the GRB explosion, at its brightest moment, it was actually as bright as the entire Milky Way galaxy. In fact, the whole picture became white for a second there. So I will play it again, and you can see it. There's a moment where it becomes completely white. Yeah. So it's extremely bright at the peak of the emission. This holds a lot of information, because when we see an object's brightness, it tells us some combination of knowledge about the distance and the energy. This is something that we know from day-to-day life. If you have a lamp in your room, it could be just as bright, provide you with just as much brightness as the sun does from outside, even though the sun is much, much more energetic, but the sun is, of course, much, much more distant. So this combination of energy and distance is what gives you the brightness, and you can have something that appears just as bright by being close by and not so energetic, or by being very far away and super energetic. And so the question was, which one of those two options we're in? And as I will show you, it's really kind of two options which are separated. It's either very close by or very far away, and the options in between are not possible. And to show that this is the case, we will use again this map of the sky in gamma rays. This is a more modern rendition of the same map. And we will show what we would expect in different situations. So this is a very basic kind of caricature of the Milky Way disk. And you can see Earth here. And imagine that the maximum distance for which you can see these events, simply because of the fact that they have a given energy, and if you put them at a distance beyond that, their brightness would be too faint for them to be caught by the detector. So imagine that this maximum distance is pretty close to Earth, much closer than the size of the Milky Way disk in any direction from us. In that case, the map of locations that you will see on the sky will be this very homogeneous map, exactly like we see. A second situation would be that the typical distance of events that you can see is of the order of the size of the Milky Way disk, or even a bit larger. In this case, you will preferentially see gamma ray bursts coming from the plane of the Milky Way, simply because there are much more stars there, there's much more stuff there, so there's more potential sources that you can see emitting. Only if the distance of events is much, much larger, not only from the size of the Milky Way itself, but also from the distances between neighboring galaxies. So you increase the distance so much that the chances of just having a random galaxy along your line of sight in any direction is more or less the same. Only then you will recover this distribution that we see, which is completely uniform on the sky. So these are the two options. If we put it in terms of numbers, the options are either that the distance is less than about 300 light years. In this case, the energy would be small in astrophysics terms, which is less than the energy that's radiated by the sun in 1 year. Or the distance would be about 1 billion light years or more, and the energy would then have to be the energy that's radiated by the entire galaxy in a year. So this is like 100 billion suns. Okay, of the two options is actually true. This was a very big debate in the 90s, and it actually culminated in this famous event that happened in 1995 at the Smithsonian Museum in Washington, DC. So this was dubbed the Great Debate of Gamma Ray Bursts. It was actually done sort of in reference to a previous great debate about the size of the universe that was done in 1920, 100 years ago from today, where people debated if we are living in just one galaxy or there are many, many galaxies, which are very distant from us, from Earth. And in this debate, there were two very famous astrophysicists at the time that debated, that presented each of these two cases, and they tried to advocate for either the close distances or the far away. The answer came about 2 years later, and this was with an interesting discovery, which is a GOB afterglow. So it turns out that after the GOB happens, you can still see some more emission coming from the same location, first in X-rays, then in optical, then in radio. And this emission, instead of lasting seconds, it lasts much, much longer. It can last days or weeks or even years. And this helps us actually discover the exact location and even the host galaxy where the GRB is happening. And it turns out that indeed these things are happening outside of our own galaxy. The locations of these two events that were found in February and May 97 were 6 and 8 billion light years away, respectively. And of course, the implication is, because the brightness is known and now we know the distance, we can calculate the energy, and the energies were absolutely huge. There was nothing more energetic than those events, except for the Big Bang. So people call them kind of like Big Bang 2 or all sorts of names like that to try and get the idea across of how super energetic these things are. And really, in terms of physics, it immediately limits the options of what these things could be, because not a lot of physical objects can actually give you that much energy in such a short amount of time. And it turns out that there are basically two options. It's either the formation of a black hole or the formation of a very rapidly rotating neutron star. So these days, we know many more GRB galaxies, and we know some of their characteristics, and we know that, for example, they're very small galaxies. They tend to be irregular. They are very actively forming stars. And this tells us all sorts of things about what is actually going on, but I will not go into this in too much detail. I just want to kind of give you the basic picture that we've understood from even just the things that we talked about just now, which are these GRBs are extragalactic phenomena. They are the most luminous explosions known to occur in the universe. They are catastrophic phenomena. They indicate the formation of either a black hole or very rapidly rotating neutron star. And in fact, we know today even better, we know that there are actually two types of events which are physically separate, but both can give gamma ray bursts of slightly different duration, but still both can give gamma ray bursts. One of these types is a neutron star merger. This is when you have two neutron stars which are in orbit around each other. Eventually, the orbit shrinks more and more until these two objects merge together, as you will see here in this diagram, in this animation. And this will create either a black hole or a very rapidly rotating third neutron star. And the other option is that you start with a star that is very massive. That star eventually burns all its fuel, collapses inwards, and what remains from the collapse creates a black hole. You will see this in this second animation. So just last kind of piece of information before I will leave you with my summary. The basic picture that we have now of these events is more or less captured in this one figure. So I will just show it quickly. You see that you have basically two channels, either the binary neutron star channel, so these two neutron stars orbiting each other, which merge and give you either a black hole or a rapidly rotating neutron star, or you have the massive star that is collapsing, which again gives you the same thing at the center. This object at the center then launches a jet, which we know must be moving very, very fast, about 0.9999 of the speed of light, so incredibly fast. And this jet happens at some distance from the source. This jet has some kind of internal process that happens, either some kind of shocks between different elements of matter that were moving within the jet with slightly different velocities, or some magnetic phenomena. This is still a topic of debate, but there's some process there that then creates the gamma rays. And the leftover energy that remains after this has happened eventually starts expanding into the surrounding area of the gamma ray burst. It comes into contact with more and more material surrounding the central object. And eventually this slows this down, and it creates these electromagnetic waves, which are first are X-rays, then visible, then radio, and this is this GRB afterglow that we talked about. So here you see some kind of very brief description of the different phases, these 3 different phases, what could be observed in each phase. This is what's written in white, and what we can in principle learn from each of those phases. This is kind of highlighted in yellow. So this is my summary. So there's still many open questions in this field of gamma ray bursts, even though we've known them now for more than 50 years. We still don't know if the object at the center is a black hole or a neutron star. We still are debating which stars exactly end up resulting in gamma ray bursts. We know some of the characteristics of those stars, but not all of them. I told you that we have to have these very fast jets. There's a question of how are they actually formed? How do they actually produce these gamma rays? This is not agreed upon. In this later phenomena of the afterglow, which is actually relatively well understood, we still see some peculiar things, like sometimes there will be a flare of X-rays coming very quickly and then going away, or the X-rays will just kind of become flat as a function of time for a while before decaying again. These may tell us something about what's going on, but still there is a lot of debate about what exactly that is. And finally, because these GRBs are happening at such huge distances from us, they could actually be used as a tool to constrain other interesting questions in physics, such as the expansion of the universe and questions in cosmology. So I will end with that and take any questions.
That was great. Thank you very much, Paz. Yeah, super good. There are a number of questions in the YouTube chat. We also, oh no, my green screen has been revealed. My secret's out.
So you're not actually in space?
I'm not actually in space. Oh, there, now I'm back in space.
Oh, good, you rebooted the universe. That's important.
Yeah. Okay.
I thought the lag was not the kind of lag I would expect from space.
Yeah, there are a number of questions. I have questions too. So I will first open it up to the questions. I like this question from longtime participant Brian Federa. Please explain the physiology whereby gamma ray exposure turned Bruce Banner into the Incredible Hulk.
Yeah, this is a top secret. I can't reveal that.
Can't reveal. That's fair. That's fair.
Yeah, we tell you, but.
Another good question from the audience: what can we learn from studying GRBs about the objects that produce them? So you kind of alluded to this a little bit, but.
Yeah, so one question, for example, is which stars end up having a gamma ray burst? Right, so first, we can study this, for example, so there's a question of how do we know this information? And then there's a question of, okay, given that we know that, what does it tell us next? So how do we know this information? We can look at the galaxies where these things happen, and we can look at the locations even within the galaxy. And we see that the type of galaxies are very, very small, irregular galaxies. So these are galaxies that are very actively forming stars. And the other thing is that even when you look within the galaxy, you typically see the gamma ray burst happening in the pixels where there is the brightest part of the galaxy. So these are really the most star-forming parts of these very star-forming galaxies. And this tells us that the GRBs are the result of supermassive stars, not just stars that are massive enough to explode as a supernova, for example, but stars that are even significantly more massive than that. So not just 10 times the mass of the sun, but maybe 40 times the mass of the sun. Another thing that is important for GRBs is that we know that in order to get a lot of energy, for example, in the rotation of the neutron star that is formed or in the black hole that is formed, we need to get rid of the envelope of the star before it collapses. And this tells us that, for example, if we have a star that has this giant hydrogen envelope, that won't do. We won't get a gamma ray burst out of that. Also, there will be so much envelope that it will be very difficult for the jet to break out so quickly, right? So this, the fact that we see the jet breaking out relatively quickly, we can constrain how quickly that happens, and we know that it has to happen within about 10 seconds, tells us that the star has to be quite compact even before the explosion. So it has to have lost all of its hydrogen, for example. And there's a type of star called the Wolf-Rayet star, which is one of the stars that is, I would say, the most likely of being a GRB progenitor, because it's very massive and it has no hydrogen. It only has this helium envelope, and maybe even helium envelope is too much.
Excellent. Thank you for that response. There's another somewhat related question. Were gamma ray bursts more common in the early universe, or are they more common today? Yeah,
it's a very good question. So they were more common in the relatively early universe, depends what you mean by early. So astronomers like characterizing things in terms of redshift. So typical redshift for gamma ray bursts would be something of order, depending on if it's a short or long GRB, but something of order 1 to 2. So in terms of how old the universe was at the time, it was a few billion years old, but it was not a baby universe. It was old, but not probing the very, very beginning of the universe.
I see. Okay. There's another question.
But by the way,
oh yeah.
Sorry to interrupt you, but GRBs for a long time were competing with being the most distant and therefore earliest events that we see in the universe. So there's always a competition between GRBs and AGNs, active galactic nuclei. And for a while, the longest distance event that we knew of was a GRB. Now it's not the case at the moment, but still we see them up to a redshift of about 10 almost.
Oh,
that's
really?
Pretty impressive. Yeah.
Oh.
These are rare, but we can see some. Yeah.
I see. But you were saying that they tend to be more frequent at like a redshift of 1.5 or 2, something like that.
Yeah.
I see.
Mm-hmm.
Okay. Would the Earth's magnetic field provide much protection from a GRB that's pointed towards us?
Great question. So every GRB that we see is pointed towards us. So these jets are very narrow, and almost all of the energy of the GRB is within the jet. And there's an interesting effect. This is an effect of special relativity, where if you're moving very close to the speed of light and you turn on a flashlight, all of the emission that comes from the flashlight is beamed into this very narrow cone. So actually, if you have these jets that are moving super fast and they emit radiation, the radiation actually only comes within the jet. If you're intersecting with the jet, you will see it. If you're not intersecting with the jet, you will see almost nothing. So basically, all of the GRBs that we see are directed at us, they're pointed at us, but they're so distant that by the time this energy reaches us, it's not that much energy, and it's not a danger. If there was a gamma ray burst in the galaxy and it was pointing at us, it could be pretty bad news. In fact, people suspect that some of the great extinctions, like the great extinction of the dinosaurs, we know that one was not the case then, but similar great extinction events could be the result of gamma ray bursts that happened in the galaxy. And if you kind of try to estimate what would be the rate of GRBs in the galaxy pointing right at us, it's about 1 every 100 million years, which is about the rate of great extinctions. So it's plausible that they can contribute.
Wow. So it's once every 100 million years that we would expect one to be pointed at us, but what's the rate?
Pointed at us in the galaxy, close enough.
Within the galaxy. what's the
ionize the
rate at
atmosphere.
which we would think that they would be just occurring at some random orientation that's not pointed directly at us? Do you know?
Yeah, so it would be about 100 times less than that.
Okay.
100 or a few hundred times less than that. And that tells you basically what the size of the beam is.
Sure.
Yeah.
Okay. So I guess you mentioned it in the summary. So we don't necessarily understand the mechanism that produces the jet that's beaming this necessarily. We know it has something to do with the angular momentum of the initial system, but we don't really understand why.
That's right. So people these days with very sophisticated numerical simulations, including, and these numerical simulations need to have all sorts of physics in them. Like basically every type of physics you can think of has to go in. So it's a super complicated problem. You need to have general relativity, you need to have special relativity, you need to have magnetohydrodynamics, all of those things together. And then you try to see if you can make actually these jets form and make them be stable and so on. And this is a very challenging thing to do. There's no way to do it kind of from scratch without kind of adding some things by hand. And so it's still unsettled exactly how these form. There are different types of mechanisms that people talk about. Some that are kind of relying on magnetic fields, others that are not. And it's not clear which one is actually taking place.
I see. Okay. Yes. One of our viewers points out that if a GRB were to occur at some point in our galaxy, 2020 would be the year that it would happen based on all the other stuff that's happened in 2020. So
yeah.
That's pretty.
I can believe that.
Yeah. Okay, last question before we move on. What's the most computationally intense aspect to modeling gamma ray bursts?
So actually, not all of the difficulty is computational. Sometimes the difficulty with these types of events is to understand what is interesting and what is just noise that is not really useful information. And so a lot of the big advances actually came not from very heavy computational efforts, but from pen and paper calculations that managed to identify what is an interesting aspect or connect a few different dots together and suddenly kind of make like some new picture that explains the few things at the same time, based on one assumption. That kind of stuff really is maybe the most useful to make progress. And that's quite difficult because, as I showed, you have this very complex behavior. So you have to be smart about how you look at the data to be able to get good information as opposed to just stuff that's useless. So I would say that's actually the biggest challenge at the moment. Because if we knew what to calculate, what to simulate, let's say, with numerical simulations, that would be less of a problem. But the problem is that we don't even know what to simulate amongst a few different possibilities at this point.
Awesome. Okay, well, that was excellent. Thank you for that presentation and for all the great information and the questions answered, Paz. We'll move on. I will let Kaylin introduce Dr. Udry. Paz, maybe you and I can step out for a moment.
Yeah, just don't get lost in those GRBs in the depths of space. Well, yeah, thanks, Cameron, and thanks, Paz, again for a really interesting talk. GRBs I study exoplanets, so GRBs are very outside of my field. And I won't lie, I was taking some notes. I learned a few things. I learned a lot of things. Don't tell my PhD advisor. So hello, everybody. Very excited for the second talk. I hope you are as well. It is my extreme pleasure and honor to introduce Dr. Arya Udry. Dr. Udry and I go way back. I think the first time we met was probably it's like 4 hours ago on Zoom when we were prepping for this event. She is an associate professor at UNLV in Las Vegas, but she's originally from France and Switzerland. And she studies geology, but not necessarily in the context that you might think. So she's a professor of geosciences, and she uses the same tools as geologists who study the Earth, but she applies them to meteorites. So you can help learn about and constrain things such as the formation and evolution of planets and asteroids in our solar system, among other things. And fun fact, she has been wanting to work on Mars since she was 15. Now, what I don't know is if that means she has wanted to work on Mars as an idea and Martian things, or if you have been wanting to work on the surface of Mars since you were 15.
Kind of both, actually.
Kind of both, okay. Yeah, well, geosciences on meteorites seems pretty darn close. So thank you, Dr. Udry, for giving our second talk here. I will go silent and let you share screen and take it away.
Thank you, Kaylin. So let me share my screen. And yeah, let's do it. So yeah, thank you very much for this introduction. I know my expertise is a little bit different from most speakers in Astronomy on Tap in the fact that I actually study rocks. I don't really study far space. I am not really good in physics and math. And so this is why I stuck to rocks. And I actually love studying rocks, and especially space rocks. So today I will tell you all about meteorites and really the basic of what you should know about meteorites. But one of my specialties is also Mars. So Martian meteorites and Martian geology. So if you have any question about Mars, please ask them, because I'm not going to talk too much about Mars today. I don't have time. I mean, I would really need 3 days. So first, why do we care about meteorites? Why do some of us study meteorites? And so obviously, as humans who want to understand our solar system, okay, what has happened 4.56 billion years ago? How has the solar system formed? How has all the different planetary bodies, and by planetary bodies, I mean planets and asteroids and comets, have formed in our solar system, and how have they evolved with time? You know, why is Mercury different from Venus, different from Mars versus different from the asteroids? And so to do that, we can explore it. We can send humans to other planets, except we haven't really done that much. We've sent humans on the moon at the end of the 60s and in the 70s, and the goal would be to send human back to the moon in 2024 if, you know, the Earth is not completely destroyed by then, because we still have 6 months in 2020. But this is all the only place humans have gone, actual humans. We have sent actually orbiters and rovers and landers all over the solar system. But we have only brought back samples from a few places. So we have brought back samples, obviously, from the moon. The humans have actually brought back samples, and the Russians have sent back samples with the lunar mission back in the 70s. But we also have samples from the tail of a comet. We have samples from asteroids. That's the Japanese space agency that has brought back some, and some more is coming back too. But obviously all this takes time, costs a lot of money. We can only go to a certain location. And so because we want samples, and we want rocks actually, and I have one here if you can see it. This is one piece of space. This is 4.56 billion years ago, billion years old, excuse me. We want to study those samples. We want to have those samples because we want to analyze them in the lab with really high precision and high accuracy instrument. And those samples will help us understanding the formation and the evolution of the solar system, and various processes such as volcanic processes in the solar system, impact processes, atmosphere formation, and possible, you know, was there life on other planets, especially, you know, on Mars, or we can even, when we go there, about Europa. We don't have samples from Europa, but so meteorites can come from all over the solar system and help us understand those really important questions about where we're from in our solar system. So where do meteorites come from? So right now we have about 64,000 meteorites. 88% of them come from the asteroid belt. So the asteroid belt, as some of you might know, it's located between Mars and Jupiter, and this is just millions of asteroids. We have about 2 million of asteroids that are more than 1 kilometer in diameter, and millions of them that are even smaller. So we find every sizes, every shape. This potato shape, this some that looks like bones, that like a femur. It's this everything. The largest asteroid is called Vesta. It's 300 miles in diameter. It kind of looks like a mushroom. It was impacted at its south pole. And we actually have 2,000 meteorites real likely from Vesta. And we've linked those meteorites to Vesta using the minerals that are in them as well as spectra. The Dawn spacecraft has gone to Vesta and has, we were able to link it to those meteorites that we thought came from Vesta. So again, most of them come from the asteroid belt, but those meteorites all have different chemistry, mineralogy, and we saw that the asteroid and the asteroid belts are all relatively different. And I will tell you a little bit more why. We also have meteorites from Mars and the moon. We don't have, nothing has been confirmed that we have anything from Mercury or from Venus. Ooh, I'm sorry. Nothing from Mercury or Venus. It's really difficult to eject something from Venus because Venus is really large, it has high gravity, and it has a really thick atmosphere, 90 times more the atmospheric pressure that we have on Earth. And then Mercury, it's pretty easy to eject something from Mercury, but the problem is that it's really close to the sun, so most of whatever is ejected from Mercury will go towards the sun and not go towards Earth, and which is also an issue for Venus. So, but we have meteorite from Mars, they're rare. There's 142 meteorites. I have 30 in my office right now that I haven't seen for quite a while. This is mostly what I study. And we'll have about 200 meteorites from the moon. And what's interesting in having both meteorites from the moon as well as the Apollo samples that were brought back from humans is that we have, how many sites? 11, 13, 12, 14, 16. So we have 6 different sites from the moon. We have the field context, which for us geologists is really important to have field context. However, meteorites come from all over the moon. It also comes from the far side of the moon and not the dark side of the moon. Only Pink Floyd says the dark side of the moon. So we have meteorites from all over the moon, and the mineralogy and the composition of those meteorites are pretty different from the one from the Apollo samples. So, again, I told you there's different types of asteroids and thus different types of meteorites. The most common type of meteorite are called chondrites. So if you find a meteorite somehow, if you're extremely lucky, you will have a chondrite. So this is, I hope you can all see, this is a chondrite. It's pretty simple. Unfortunately, I wish you could see better, but there's little specks of metal in it. This is very typical meteorite that you will find. So what happens is, how do we form that? When the solar system was formed, you had what we call the protoplanetary disk, which is pretty much a plane that was rotating fast. And in the middle, you had the proto-sun, the baby sun, that was growing. And in this cloud, you had gas and dust. As the time passed, still really early in the formation of the solar system. As the time passed, the temperature cooled down. As the temperature cooled down, the gas will condense into minerals. And those tiny minerals, those still really dust, is going to start agglomerated and collide with each other to form dust, then grains, then little pebbles, then boulders, then asteroids. Okay? And those happen, all of this happened in the protoplanetary disk. So the chondritic asteroids represent pretty much this agglomeration of all those different components that form very early in the solar system. Okay, some of them have not changed at all, which is completely crazy. This is what a chondritic asteroid is. It has just not melted. It is really, it's a space sedimentary rock. Yeah. So this is the most common type of asteroid. But there's another type of asteroid that we call achondritic. We just add an A in front of chondritic. So what happened is, once you form those chondritic asteroids, especially very early in the solar system and all the asteroids that were closer to the sun, there was a lot of heat that was provided then. You had what we call short-lived radioactive nuclides that emitted heat at the time and helped completely melt those firstly formed chondric asteroid. When you completely melt your asteroid, you have what we call, it's going to be a magma ball, if you will. And when you have this ball of magma, the heavy element will sink at the bottom and the light element will float. And this is how you can have a structure within asteroid and within planets. As some of you might know, the Earth has a core, a mantle, and a crust. And that's the same for the achondritic asteroid. They have a core, a mantle, and a crust. And we know about our own core using the core of asteroids, like this guy right here. This is all metal. I can show you more after if you would like. So those are the two different types of asteroids that we have, and that's the two different types of meteorites that we have. So how do we obtain meteorites? There's different ways. So as I quickly mentioned before, what happens is that you have a meteorite likely from somewhere else in the asteroid belt, coming, impacting your planetary body. It can be an asteroid, it can be Mars, it can be the moon, at a speed high enough that will eject a piece of that planetary body. And that speed will differ depending on the gravity, which what we call the escape velocity, which will depends on the gravity, so the size of your object, how much atmosphere there is. And so once your piece is ejected into space, it will float into space, and then at some point, if you're lucky, will land on Earth. We have meteorites landing on Earth all the time. I believe it's like we have 100 tons per year of meteorites. It's huge, but most of it will fall into the ocean because most of the Earth's surface is the ocean. So where you could find meteorite, you can find it anywhere, but it's not really easy to distinguish from the other rocks that we have on Earth. So what you have to go is in the desert, in hot or cold desert, where there's no vegetation and no other rocks. So for me, as a scientist, how do I get my meteorites? So there is this expedition that is funded by both NASA and NSF that goes to Antarctica in December and January and brought volunteers, usually planetary scientists, meteorite scientists, and mountaineers, so 8 people usually. And what they'll do, they go in Antarctica in the middle of it, camp in the middle of nowhere, and what the ski-doo, as you can see on that image, will go as a grid and we'll look for meteorites. Anything that stick out of the ice could be a meteorite. And you can see right here, this is my friend Nina Lenza from Los Alamos National Lab. She actually might give a talk next month. But you can see that this kind of darker rock in the middle of the other rock, that is a meteorite. And so those samples are then sent back to NASA Johnson Space Center in Houston. And myself as a scientist, I can write a proposal explaining what I will do to this meteorite, what's the goal of my research to get a loan of it. So I can have, a gram of that meteorite. I can have a thin section that I will then, it's just a very thin slice of this rock that I can then look under the microscope and do chemical analysis. So I have some of those in my office right now. But we can also find meteorite in hot deserts. So mostly in not South Africa, in Northwest Africa, mostly Morocco, but also in Algeria and Tunisia. Locals are actually trained, that's a full-time job, to look for meteorites in the desert. And you can see right here, you see this meteorite has what we call a fusion crust. A fusion crust that you can also see in this meteorite, this is this kind of black, and in this case, this is black. Sometimes it can be slightly different color, more greenish. Exterior, and this is formed from entry into the atmosphere. Your meteorite will start melting, and this is the result of melting of this meteorite. So the locals in the Saharan desert will go look for those meteorites, sell them to dealers that will then sell them to me. A Martian meteorite is about $1,000 a gram, so I cannot buy too many of it, obviously. And I have my dealers, my meteorite dealers are really well known in the community, and usually go to conferences too. So they're not random dealers. So what do meteorites look like? So I show you have the chondrites The chondrites, again, are the most typical type of meteorites. Again, this is one right here that I bought. This is actually pretty cheap. I bought it for $100, you know. And again, this is the oldest object I will ever touch, which is 4.56 billion years old. It's kind of a shame that you're not, you know, there and to touch it. But this is, again, the most common type of meteorites. A lot of people think that the iron meteorites, that only form of iron and nickel alloy, is the most common type of meteorite. That is not true. Usually it's about 5%. I think it's about 5% of meteorites. And you can see here I have a slab of it. You can see this is all metal. I hope you can see from the reflection. And I can put my full screen after if needed. One of my favorite type of meteorite. So actually, what I forgot to tell, those iron meteorite represent the core of those achondritic meteorites. So this all the heavy element that concentrated in the middle of this magma ball once the asteroids were completely melted. And then there's some really funky one that we call palisite, and those are my favorite. I hope you can see it. So you can see in there, there's metal. And then this mineral that we call olivine, also for those who know the gems, this is called peridot as a gem. This is this green mineral you can find like all over Hawaii. You know, any basalt, you'll find that. Crater of the Moon in Idaho, a bunch of basalt that you will find also in the Cascades. Yeah, both metals and minerals in it. Some people said it was the core mantle boundary, and some people said that it might have formed from impact. Those are really pretty. And then the other kind of meteorite you can have are the lunar meteorites, and the Martian meteorites are not that easy to recognize in hand sample. You usually need to look at them under the microscope or do chemical analysis to make sure to link them to those planets and moon. And so what I want to teach you a little bit is, do I have a meteorite or do I have a meteor wrong? This is how we call that. You know, I live in Nevada, and Nevada, it's a lot of desert. There's also a lot of mines. Slag, which is the result of mine waste, really. Slag is mine waste, mostly made of iron, a bunch of other stuff. Look a lot like a meteorite. For some people who are not used to them, they are not. So meteorites, usually, as I showed you before, will have this fusion crust, this top exterior that's melted. Okay, but this fusion crust is usually relatively smooth. It's not going to be square. It's not going to be completely rounded like it's been altered by water either. As you can see on this left image, okay, you can see that slag, it has those pockets that you will never see. It's those holes that you will never see in a meteorite. It also that slag has a really weird shape that's going to be pretty rare also in a meteorite. The meteorites, what you will see, you could see little specks of metal. So if you cut it, you should see little specks of metal. And the fact, you know, the chance for you to have a meteorite is usually going to be a chondrite. Chondrites have those little spherules in it that we call chondrules. So if you use a hand lens, you should be able to see those chondrites and this metal. So it's going to be a little bit dense. But slag can be also very dense. A lot of Earth's rocks are also magnetic. That's very common. Even granite, the granite that you'll find in the Sierra Nevada, will have what we call magnetite in it, which is a magnetic mineral. So this could be easy to mix up. What you can also mix up the fusion crust with is desert varnish. Desert varnish is formed from alteration of rocks in the desert that also has, I think it's due to microbial alteration. So it's good not to mix up. So I think this is it for my talk, and I'll take any question. Thank you.
Great. Thank you, Dr. Udry. That was fantastic. I'll kick it off by saying, yeah, since your screen was kind of tiny, would you mind, now that you're a larger screen, showing off some of those meteorites so we can see the detail?
So this is the chondrite, the very typical one. I'm sorry if the light is not great. Let me try to play with mine. So you can hopefully see the metal. I mean, it's a little bit altered, this one. You can see the metal right there. it's hard to see the control. Let me see. There's some spherals, and some of them, I have a beautiful one that will be very rare. I bought it just to see it, but hopefully in this one, I don't know how well you can see, but you can hopefully see some little spherals in it. Those are called chondrules, and also were from very early in the solar system. This one right here is really cool. This is this iron meteorite. This is iron nickel alloy, and this really likely represent the core of an asteroid. This is a slab. This is just a slab of it. It was cheaper. And then my favorite, the palisite. So hopefully, maybe I can do something with my so hopefully you can see, yeah, you can see the metal. So again, this is a slab. So you can see the metal, and then what we call the olivine, those minerals that you find in the mantle of the Earth's mantle, the Mars mantle, and a lot of asteroids. Olivine is all over. This mineral is all over the solar system. So yeah, so those are the samples I have.
Ah, that's very cool. Thank you for sharing. So that segues into one of the questions that we had in the chat. Joseph Karpinski asked, do you collect many meteorites from Antarctica?
I don't personally. I haven't gone yet. This is something that has been hard being tenure track to go to Antarctica. I'm actually supposed to go to the Atacama Desert in the end of October, if, you know, again, the world is still existing, who knows at that point. And so we go to the Atacama Desert because, again, there's not much else than that's a desert. There was a really large amount of meteorites discovered there. I think there was just a fall of, you know, kind of a rainfall of meteorites. And so we'll try to go collect them there. Antarctica is just more, I mean, it's been canceled next year. But my PhD students ready to go.
Oh, that's exciting. That's quite a trip during your PhD. Let's see, we have Jim Hendrickson was asking about Ceres. So it was somewhat recently reclassified as a dwarf planet. He's asking, is it also still considered an asteroid? How does the human classification reflect or change our understanding of the object?
Maybe you astronomer, it is a dwarf planet. This is why I did not include it as an asteroid, because it's been classified dwarf planet. So I don't think it can be both a dwarf planet and an asteroid. Maybe you astronomer might, you know, you have the strict definitions, so you might be able to help me with that. But no, Ceres is actually larger, much larger than Vesta in diameter. I believe it's 900 kilometer in diameter, but it's rounded. I mean, it's a rounded object. So,
yeah, for anybody wondering about astronomers and their classification schema, trying to make method out of the madness, I apologize in advance. Good luck. After black hole, we stopped naming things accurately. We got a couple more questions. So Jasmine Saif, I hope I'm pronouncing that correctly, asked, how do we know that a meteorite is from Mars or from somewhere else?
That's a great question. So we can use different forensic tools for that. If we just take as an example Mars, Mars was, you know, it's different from most of the meteorite that we have. My PhD advisor is pretty old right now. When he was finishing his PhD and had nothing else to do and looking at this whale meteorite that was very young, seemed to come from its chemistry, its mineralogy, kind of showed that it came from a large body, a large planetary body, and not an asteroid, which was very different from what we had at the time. That was at the end of the 70s. So there was a paper that came out that proposed that it came from Mars, because that was the most logical explanation. It was a large body, but it had to be, you know, further away from the sun than us, because everything that's closer to the sun should be going towards, all the meteorites should be going towards the sun. So the evidence that we knew that those meteorites, those whale meteorites were from Mars, is that the Viking landers landed on Mars in 1976 and measured the atmospheric composition of Mars. In those same meteorites, you can look at this little gas pocket within the minerals that you find in those meteorites. they measured the composition, and it was the exact same one that the Martian atmospheric composition. So that was the first evidence those meteorites come from Mars. In addition, what we use now are those kind of different ratios. So we'll use iron manganese ratio that will be different from Earth, the Moon, Mars, and Vesta, also the largest asteroids. We can also use what we call the triple oxygen composition, isotopic composition. So oxygen has different isotopes, and those isotopic composition will be completely different throughout the solar system. You have different pockets, and this is how we can also say, like, okay, this rock has the same oxygen isotopic composition as this other rock, so they have to come from the same planetary body, asteroids. So now this is how we checked. So for example, there's this, just 2 hours ago, I was looking online on Facebook, and there was some of the dealers that were selling one that looked like it could come from Mars. And I asked, like, did you check the oxygen isotopic composition? It's like, not yet. And this will be definitive that if it comes from Mars or another type of asteroids, or if it's linked to something else.
Okay, yeah, so this isotopical composition analysis is really kind of the primary method for...
Exactly. Now, it's cheap too, compared to looking at gas composition. But then now, if you give me a Martian meteorites that look like the other, I can look at it on the microscope and immediately I can tell you.
It's so funny. Every time, we're talking about dealers and you're saying it's a solid $1,000 per gram, and I'm like, no, we're talking about meteorites.
Yep.
Very family friendly.
Someone mentioned Nuclemen. It is one of my dealers. I have a package from him coming from friends.
That's so funny.
That's funny.
Oh gosh, we have a lot of good questions. Carnatrice, is that all one word? Cooker. How do I spot the difference between meteors, comets, and asteroids in the night sky?
So if you have an asteroid coming for you will die. So an asteroid should not crash on you. If you will, a meteor will be a piece of an asteroid that detach and then come. If you have an actual asteroid, it would be bad for us. Really the difference, I don't know how well you could see really in the night sky, but a meteor, you will see really a fireball, whereas a comet, and I don't do that much observation, but a comet will have a tail. Because a comet is actually mostly ice with dust in it. So as it comes closer to the sun, the dust will vaporize, if it's the right word. So you have what we call a dust tail and an ion tail with the interaction with solar rays. So that's the way you will compare them. I have not done much observation, but I've seen a lot of fireballs, and I almost crashed my car many times in Vegas, seeing like a fireball in the sky. So
wow.
You can see that.
Yeah, and it's been a while since I've studied planetary science, so correct me if I'm wrong, but these two tails for comets, there's the dust tail and the ion tail, as Arya was mentioning. The ion tail generally always points away from the sun, right? And the dust tail points in the opposite direction as the direction of motion of the comet. Is that true? So you can get some interesting angles?
They're not, I think they just have a different angle.
Were they just different angles? Oh, okay.
Yeah.
Okay.
I think because, yeah.
Okay. Let's see, we have a couple more questions. Yeah, can lunar, this is Vincent Mujica, sorry. Can lunar and Martian meteorites be linked to specific sites on their respective planets and moons? Also, by what mechanisms do meteorites leave their parent bodies?
So again, how they leave the parent bodies is it had to be ejected by something else. So you have to have meteorites impacting the surface of Mars, the moon, or asteroids to be able to eject a piece of it. That's how it works. So we are trying as much as we can to link them to specific sites. It is very difficult because it has to have the same age of crystallization. When did the rock form? When did the rock escape the planet? What is the mineralogy and the composition of those rocks? And all of this is very difficult to link to specific site. We have some ideas of general broad sites, but we have not linked definitely to a specific site on the moon or on Mars. there is a lot more work to do. There is, we need higher resolution instruments, spectrometer to determine that. But yeah.
Okay. I see too, I have a correction on my pronunciation. I was wondering if that was Carnot, but I wasn't brave enough to suggest it's Carnot rice cooker. So we have a physics fan out there. We'll do one more question. That's a lot of questions. This is great, so much enthusiasm. I will go with Suhal Fayej. What is the largest meteorite that you have studied, and have you gained any unique insights from studying it?
The largest, so the thing is, just for you guys to know, I always study the same amount per meteorite because it's so rare, it's so expensive. I usually study a lot of thin sections, so I can thin slice of those meteorites under the microscope. And then sometimes I have a gram of those meteorites, and that's it. I do not buy the entire meteorites. I am not rich. This is research money. The largest I have was what's called NWA, that stands for Northwest Africa, 7034, and it's a really weird Martian meteorite. The total mass of it is 9 kilos, which is huge. Wait, was it 9 kilos? I think it was 9 kilos. I don't remember the exact mass because I don't see it. But this meteorite is really strange. It's very old. It's the oldest that we have. There's so much that we've learned from Mars from it. Different composition, different mineralogy. Mineralogy composition that we did not expect that formed so early on Mars. But that has nothing to do with the size. It was just really cool. And quickly, Jasmine had a question. There are a lot of meteorites and we don't know their origin. It's just, they're not linked to each other, or they're not, we cannot necessarily, there's so many asteroids, we cannot necessarily link them to a specific asteroid. So what we call them is on-group achondrites. Like this brand new one I was talking about 2 or 3 hours ago, we still don't know. We might know soon, but there's so many meteorites too.
That's kind of exciting. You're right in that moment of, a thing exists, but you don't know, kind of much or certainly not everything about it. And that, that's a lot of the interest in science, is the middle part. That's cool.
And I can continue to answer a question on the chat, maybe, is that?
Yeah. If you and, I didn't think about that, but yeah, Paz and Arya, you both can kind of chat at some of the specific questions. There are several that we didn't have time to get to. So that'll be our last question so that we have enough time for trivia. That'll be our last science question. I noticed that somebody has asked a question for me twice. Let's see, Jocelyn Emsley. Question for Kaylin, tell us about wingspan. So given that I'm on the moon, I was very confused as how somebody was asking me about wingspan. I don't even think I have a copy in my bedroom, which is where I am. Wingspan is a bird-based board game by Elizabeth Hargrave that it won at least one Game of the Year award in, I think, 2019 was when it first came out. And earlier this year, there was a European expansion that came out. You build, is that the right word? You build birds, you get points for birds, you learn about birds. There's a lot of beautiful art. It's super fun. And it's keeping my sanity at whatever level it normally is.
You build birds?
Well, you don't grow them. I don't know what the right verb is, but you create birds. You get more and more birds. You have to feed them resources, and they take eggs because that's where birds come from. And then they have abilities that help you to get other birds. And birds are worth points, but other things are worth points. Oh, it's super fun.
This sounds weird.
You're weird. Birds are fun. It's a great game. Anyway, I highly, highly recommend it.
We've been on.
Always get the bird selection is somewhat random, but the raven is way OP. So if you get that, keep it. All right, if we can, let's give a round of applause to both of our speakers. Thank you again.
Good job, guys.
Paz and Arya. That was really great.
Thank you very much for joining us.
All right, are we ready for trivia? Should we give this a shot?
Yeah, pub trivia. Let's do it.
Okay, can I share screen? Yes. Okay, we're gonna see. Hopefully this works. So I'm gonna share a desktop, and then I'm gonna hit play. Let me know if this works. So do you all see?
Yes.
Like actual PowerPoint slide display?
No, we see your.
Do you see the secret? The secret sauce?
Yeah. We're seeing next
All right,
slide.
Yeah,
We're seeing
let me.
presenters' notes.
Okay, I'm gonna stop sharing for a second. I'm gonna change a setting. There's 3 different options, and
Can't reveal all the answers to our.
yeah. We don't want. Okay, I'm gonna try monitor 2. That's what we're gonna go for. Right.
When you generated the painting of the gamma ray burst that's in your background, is it oil? Is it acrylic?
It's acrylic. Yeah.
Cool. That's very cool.
This was my gift to my PhD advisor when I finished.
I see.
So I don't actually have
presumably we won't have the potential to do an observation like that at any point in the distant future.
Yeah, that's right. Although one thing I didn't mention in my talk is that 2 years ago, I guess 3 years ago now, we saw the first GRB through gravitational waves. And that actually is a way to see GRBs not along the jet, or the side of the jet. So at least the geometry that's here is not impossible now, but we can detect gravitational waves.
But it can be detected, but not visualized in a way that we're familiar, have an intuition with, like electromagnetic waves.
Right, and that one was the second closest gamma ray burst that we ever detected, and it still was at a distance of 100 million light years from us.
I see.
So it's pretty far away.
Okay.
See, are you all seeing the right?
Now it looks correct. Yeah, Caitlin.
Ooh, okay. So we're going to try to use a site called polleverywhere.com. This is what we tried last month, and it seemed to work out pretty well. It makes the trivia more interactive and thus hopefully more fun, and maybe even the same amount of educational. So if everybody could, in a separate browser window or a separate browser tab, if you're on your computer, go to pollev.com/AOTLA. So that's Astronomy on Tap LA. And if you're not on a computer, you can still play along, and you can type answers to the different questions in the YouTube chat. We'll be monitoring that as well. So I'll give everybody kind of a second to do that. All right.
This will give you a method by which you can respond, but also see the responses of other people.
Yeah. So we've got the first. Oh, looks like my screen's sharing. Hold on. I think I need to change which screen I'm sharing one more time.
Oh boy. Right. Here we go.
1 second. Technical difficulties. We're gonna get it.
We'll get it.
Let's see. We'll get it. We'll get there. I see that people are already answering. That's great.
Oh, good.
See, are people seeing, what do y'all see right now? Is everybody seeing the actual answers? The poll results?
I'm just seeing the options. I don't see the results.
Okay, I'm gonna go.
Maybe we should ask the question to our audience explicitly.
Yeah. So while we're troubleshooting this, I'm gonna unplug from my second monitor. So the first question is, roughly how many total meteorites have ever been recovered on Earth? Oh, can you guys hear me? I think I lost it for a second.
I can hear you.
Yeah, we can hear you.
Okay. Okay, let me try one more time. I think we can get it.
All right. We see presenter notes.
Yeah, let me see. All right. Let's see, this worked last time. What am I doing wrong? Yeah.
I'm gonna stop my share. There we go. Is that working?
Yes, now I can see
Yay. Okay.
options and what people have voted.
Thank you, everybody, for bearing with the technical challenges. So roughly how many total meteorites have ever been recovered on Earth? So this is building off of Aria's talk. The options are 64,000, roughly 128,000, 256,000, and 1 million. And while I was getting my technical difficulties sorted out, it looks like we have about 3/4 of respondents, about 71%, who think it's the small number. And that is actually correct. It's about 64,000. 1 million, a little bit of a high ball. 256,000 is gaining traction.
It's rising. It's rising.
Not quite correct. Yeah, so it's about 64,000. And here, well, the next slide. This is actually a video of a meteor.
Holy.
Oh, I forgot the video, the audio was on. This is a bolide, so a very bright meteor that's streaking across the sky. This was actually 14th of June, so not that long ago, a little bit over a week ago. I'll play it again, over the sky in Western Australia. So this is called AMS Event 2881. I didn't know what AMS meant. It's the American Meteor Society. And you can just see what makes this so remarkable is how incredibly bright it is, and how long lasting it is. And you get a cool green flare there as well. I'll show it one more time.
They happen more often than we think. Like I said, like driving home from work, I've seen at least 5 times in Las Vegas sky, which is not the darkest sky in the world. Several fireballs that were pretty impressive.
That's true. And I guess like it's interesting now that pretty high quality video cameras, let's see if I can just keep playing this, have become commercially available in the past, I don't know, a couple years or a couple decades. You know, many more of them seem to be getting caught on camera. There's an internet famous dash cam one of one in Russia from, I don't know what that was, 4 or 5 years ago.
Yeah.
Yeah, it's kind of cool. It's very, very impressive. All right, who is ready for question 2? Go ahead and get it started. So, NASA renamed its WFIRST Space Telescope to honor what person who is NASA's first chief astronomer? Again, it is NASA renamed its WFIRST Space Telescope to honor what person who is NASA's first top astronomer? So this is it's kind of a short answer. So you can write in answers. I have a moderation feature set. So if you try to write something inappropriate, it will not work. So it's a family-friendly program.
And this happened last week or a week and a half ago, right?
Yes, this is very, very recent. Jim Bridenstine, the current acting officer, made the announcement. Yeah, I think last week or maybe 2 weeks ago, certainly just earlier in June. All right, so Nancy Grace Roman, ooh, somebody upvoted, somebody else downvoted.
I got a vote.
Mike Pence. Spoiler alert, Cameron Hummels is incorrect.
Ah,
I don't mean to, burst the bubble.
Like that.
So we've got a lot of votes for
Nancy Space Telescope, CHST. I like that.
You mean the Kalen Henderson Space Telescope?
No, not the Kalen Henderson, the Cameron Hummel Space Telescope.
Yeah, it's a common mistake. Let's see, Nancy Grace Roman. We've got Hubble, we've got Spitzer, we've got Webb, Roman for short. Seems that people are roughly maybe converging. So there is a Hubble Space Telescope. There is a Spitzer Space Telescope. But the true answer here is Nancy Grace Roman, or it's known as the Roman Space Telescope for short. So Nancy Grace Roman She was a U.S. astronomer. She only died a couple of years ago at the age of, I think, 93. It's kind of amazing. And she had, so her research when she was at, what was it, Swarthmore and then Yerkes, she studied stellar classification and stellar motions, made a couple of seminal contributions in that field. And she later, as the question mentions, became NASA's first chief astronomer. And it was while she was in that position that she was one of the key players, one of the foundational people who actually planned for and set up the Hubble Space Telescope, which is arguably the most famous space telescope. So she is a badass. So I have a video here. Let's see, I'm gonna turn off the sound. This is not explicitly about Nancy Grace Roman, but this is about the the Roman Space Telescope. The announcement is very new, so I'm still not always remembering the change. So it is a space telescope that combines the same hardware and instrumentation needs for two very, very different fields, but that happen to be the same into one space telescope. So the search for dark energy, and specifically using gravitational microlensing to search for exoplanets, it turns out they both benefit from having a very, very wide field of view camera, which you're seeing here with Hubble in the upper left. The Hubble field of view being about 100 times smaller than that of Roman. So wide field of view and observations in the near infrared. So we're talking roughly 1 micron wavelength of light. And so again, its goals are to study dark matter using a couple of different techniques, and also to pick up where the Kepler Space Telescope left off for inner planets, and to do what we call a statistical census of exoplanets for outer stellar system architectures. And here's a neat little animation showing how microlensing works. Yeah, I'm seeing there's still some answers popping up. It is not Princess Leia. It is not Princess Leia. That's a good guess given our love of Star Wars. All right, let's go ahead and get to the next question. Oops. All right, what solar system moon was recently found to be moving away from its planet, Saturn, 100 times faster than previously thought? So again, that's what solar system moon was recently found to be moving away from its planet, its host planet, Saturn, 100 times faster than previously thought. All right, what does everybody say? Ooh, it looks like we've got a lot of, oh man. Well, so I made this one a word cloud. Okay, yeah, there we go. We've got a bunch of different answers kind of floating in. Somebody wrote, this isn't going to show up well in the word cloud, but somebody wrote Titan moon, best moon. The answer is not moon. There's only one moon named Moon. The answer is also not best. All right, but it really looks like there's a lot of love for Titan. Titan. Oh, okay, somebody coming in with Enceladus. We've got Io, Charon. Charon, I think, is it true? Is Charon, at least for a dwarf planet, the moon that has the highest mass ratio with its host object? I think that's true.
I think it's called I think people are referring to that as a dwarf binary, because the mass ratio between Charon and Pluto is around 3 to 1 or 2 to 1.
Yeah, I was gonna say, I think it's 2 to 1, yeah.
Yeah. It's
kind of crazy. Yeah, you can see we've got a Pink and a Floyd. Those were not separate answers. So it looks like the wisdom of our Astro and Tap community is good. The answer is indeed Titan, and it is not supercalifragilisticexpialidocious.
Seems like the spelling is good on that one. Good job.
That's impressive. I don't know who wrote that, but that is quite impressive. All right, yeah. Oh, we've got another answer, Endor. Endor. Ooh, that's tough to say no to that. Iapetus, Tethys, a lot of good guesses. A lot of good guesses out here. So what I'm showing here, we're looking at on the left. This is actual composite image, the images, mosaic together, taken in the near infrared, and you can see some features labeled, including Xanadu close to the south pole of Titan as it rotates. So that's very cool. And on the right, we're seeing a top-down view. I don't know if those stars are accurate, but a top-down view of the moons of Saturn and what their orbits, how their orbits look. So you can see roughly circular, at least the ones that are drawn are, you can somewhat tell from this angle that they appear to be coplanar. And Titan is in red. And so what people found looking at observations over a span of, I think it was at least 10 years, I can't remember, but basically that Titan, the orbit of Titan is expanding. So it's drifting away from Saturn, having a wider and wider orbit, wider than people thought, again, about a factor of 100.
Do we know the time scale at which it will be ejected from the system and lost?
That's a good question. I do not. I can't remember if that was discussed in the article. I mean, probably.
I mean, if it keeps up at some point, I mean, because Titan's super large, largest moon in the solar system, it could be its own object, but probably it would be ejected and then crash into something else and make some wonderful meteorites. Wonderful space rocks.
Yeah, so I wonder, this is probably crazy. I wonder if you ran enough simulations, would there be any in which it would be ejected from Saturn and captured by Jupiter as a moon? Probably not. Probably the angles just don't work out at all.
No, I don't know. Possible.
No. All right, let's get
what's
to
next.
Yeah, what's next? All right, last week, what Russian-German project released the deepest all-sky map of the X-ray sky ever taken?
Ooh.
So again, last week, what Russian-German project released the deepest all-sky map of the X-ray sky? So how does the sky look in X-ray wavelengths ever taken?
Hey, Paz, can you chime in? What's the energy difference between what one would normally consider to be an X-ray photon and what one would normally consider to be a gamma ray photon?
Yeah, so that's somewhat arbitrary, of course, because it's a decision in the end. But typically, it's a few tens of keV, of kilo electron volt.
Okay.
So that's more or less where people put the cutoff. Some people would put it at 10 kilo electron volts. Some people put it at 30. That's kind of where it is.
Do we have, what's the high end of what we're capable of actually detecting in the gamma ray spectrum? Like, we must cap at some level, right?
Yeah, so the highest energy gamma rays, so I actually mentioned in my talk that gamma rays are typically seen from space. This is true for the most part, but if you go to very high energy gamma rays, that's not true anymore. And the way that you detect them is actually, you detect the cascade that happens once they go into the atmosphere. And so there's a cascade of particles that are created, secondary particles that are created. And you can infer the energy of that gamma ray that came in contact with the top of the atmosphere. And then you can go to super high energies. You can go to PV and even more than that.
I see. Sure, sure. Interesting.
Yeah,
Some good answers.
Yeah, we got the Death Star, we got Val Kilmer, we got Borscht Sauerkraut. Contenders, but not correct. The correct answer, and we see a bunch of people kind of zeroing in on this, is indeed Eros-Zeta.
Eros-Zeta, yeah. Yeah, this image is incredible. This is by far the deepest image of the X-ray sky that we've seen. Prior to this, the results were from an X-ray telescope, space-based telescope called ROSAT from about 30-ish years ago. And this is like 10 times deeper than that, better angular resolution so you can see smaller objects. And you can see all sorts of features here.
Yeah, I brought it, I'll bring up the next slide.
Oh, do you have the annotated one? That's really nice.
Yeah.
Yeah, so obviously this is in the same projection that Paz was showing before with the projection where the Milky Way makes the line across the midplane, kind of the equator of this projection. And but you can see you can see lots of small scale structures that are all identified. Then you can see this very large scale structure that's kind of centered on the center of the Milky Way, which is in the center of the projection. So it's labeled here as the North Polar Spur, but this is like a bubble of hot material that's blowing out from the interior of the galaxy, and is presumably due to correlated supernova, and they're all ejecting stuff at the same time. And so you get this kind of this large bubble of material that's projecting outward, or it could be from I don't know, an explosion from our supermassive black hole in the center of the galaxy at a long time in the past that's slowly percolating out into the outskirts of the galaxy. But this is really amazing. And this was only after 6 months of observation by the eRosita team. And it's going to be up there for another like 5 or 6 years doing more and more of these and getting deeper and deeper and higher signal. So it's super exciting. I'm not even an X-ray astronomer, and I'm super excited about this.
I mean, these are the kind of images I think of this, and I think of all my observations of protoplanetary disks and ring structures, that it's so difficult for me to believe that it's data, because it's just so incredible.
Yeah.
And it's so pretty. It's so cool. Oh, that's cool. So you said this is about 6 months, and it's going to be up for about 6 years?
Yeah, I think they're planning to have 7 more images with this amount of depth that they'll then co-add into a larger data set. So the way the co-adding works, it'll end up, the final product will be about 5 times more deep than the current observations show here. And most of the observations that are being detected in the X-ray, and most of the objects that are emitting in the X-ray are like X-ray binaries, so stars that are emitting in the X-ray. Not many stars do, but some stars in certain circumstances do. Those would primarily be within our galaxy, but then also the bulk of the things that we're seeing here, the little dots that are everywhere, are active galactic nuclei. So those are supermassive black holes in other galaxies that, as they have material funneling onto them, they emit in the X-ray. It gets hot enough to emit in the X-ray. So most of the objects, I think it's like 80% of the objects in this image are coming from the supermassive black holes in other galaxies. But you also see X-ray clusters and what's that?
I was just saying that's so cool. You know, all of these little dots that look like stars, you know, are actually supermassive black holes.
They're supermassive black holes in other galaxies.
That's just awesome.
It's pretty sweet.
Oh, thanks for giving the download on that. That's really
yeah, no worries.
All right, let's get to the next one. Oh, people are already going.
Nice.
All right, so yeah, yesterday morning, an annular solar eclipse was visible over parts of which continents? So yesterday morning, so this is the morning of Sunday, local time, an annular solar eclipse was visible over parts of which continents? So I thought about leaving a couple of them off to be tricky, but then I decided this was probably actually trickier. Let's see, no love for Antarctica.
Yeah, it had 1% a second ago, and I guess
somebody was like, I'm out. No meteorites, no annular solar eclipses. So the answer, does anybody on the call know how many continents, or has a guess? Anyone who doesn't know the answer?
I thought it was 2, maybe 3.
Yeah, it is, at least what I was reading, and maybe this is disputed depending on Southeast Europe, but that it's 2, so Africa and Asia. So going
that's what I thought.
Solidly over the Middle East, catching India, catching Northeast Africa. So what we've got here are a couple images. So the left is just a super cool image taken in Yemen. And you can't quite see kind of I don't know what the right phrase is, the actual ring of fire that defines the annulus. But then we have on the right-hand side, a couple of stills taken from a project in India to study the ring of fire. And there you can see on the almost kind of perfect annular ring right there.
Yeah, that's cool.
It's really, really, yeah, this is great. I can't remember, when is the next, so I know the next total eclipse that's visible in the US is April 8th, I think, 2024, but I don't know when the next annular solar eclipse visible in the US.
I don't think we have any annular before then. I might be mistaken. Do you guys know? Paz or Arya? No.
I'm not sure. I think, yeah, that's us.
Yeah, I think I was reading that the frequency, based on how the kinematics and geometry work out, the frequency of total solar eclipses is, if I'm remembering right, maybe once every 18 months, kind of
roughly. Yeah, that's right.
I imagine annular more common.
I mean, for it to be total, it just has to be let's see, the orbit. The moon has to be closer to us than it normally would be, so it needs to be near perigee. Whereas if it's near apogee, it's farther away, then it's angularly smaller, so it covers up less of the sky, so you see more of the sun. I think it's.
I figure since it spends more time in that orbital phase, that those might be.
Oh, that's true. It does.
But beyond that, I'm not sure.
Laura May says October 2023 over the US.
Oh, really? Okay. All right.
That's cool. So we've got, in a 6-month span, we'll get, so October, we'll get the annular, and then the following April, we'll get the total. That's cool. All right, everybody ready for the next one? All right, when was the first gamma ray burst discovered?
See how well people were paying attention.
Yeah, ooh, okay.
Strong response.
Strong early move.
Strong response.
1947, 1953, 1967, 1981. Okay, 67's got some competition. 47 has more competition. Thought about making this one a choose your own year, but that seemed mean. 53, 81. Okay, it seems that there's an overwhelming preference for 1967, which, drum roll please, is correct. So I found a video of, a rendition of a gamma ray burst, and I don't know anything about gamma ray bursts, so maybe we'll have to rely,
Well, you do now because you listened to the presentation.
Sorry, I know more about gamma ray bursts.
Gosh.
I know enough to admit that I don't know very much. But so here we've got some.
Yeah, so this is the formation of the jet.
Oh yeah,
this is from the supernova creation mechanism as opposed to the binary neutron star mechanism.
Exactly. So this one is the collapse of a massive star. So you also have a supernova. We are actually looking at it from outside of the envelope of the star. So you see the jet emerging from the envelope, but you don't actually see like the inner part where there's the black hole. And this is now the jet from a larger scale, and just looking around it. And you see
yeah,
super bright on the center.
Yeah, I hope everybody had their gamma ray burst glasses. They're like solar eclipse, only light. All right, ready for the next one? Let's do it.
Yeah.
Let's see. Oh, come on. All right. In April, what NASA mission currently traveling through the Kuiper Belt teamed up with amateur astronomers to visualize the parallax of Proxima Centauri? So what the question is looking for the NASA mission. It's currently pretty far away. Ooh, New Horizons, New Horizons, New Horizons. Oh man, I thought this one was going to be more difficult by making it a short answer, a Q&A.
You make your questions too easy, Kalen. I think that's the problem.
yeah.
I always make these quiz questions like a PhD defense. That's what I try and make it challenging. I guess
if I had a nickel for every time.
What's that?
I said if I had a nickel for every time I heard that my questions were too easy, I think I would have the same number of nickels as if I got a nickel for every time I was told the questions were too hard. I would have equal piles of large numbers of nickels.
Oh, Okay. All right. Although I suppose right now everyone has access to the greatest database in the history of the world, which is to say the internet. So everyone can be right all the time.
Oh yeah, I guess we should have given a more explicit disclaimer or a preference for people. You know, this is honor system and there's no prizes. So, you know, what are you gaining by looking at Wikipedia? The correct answer is New Horizons. And so here, let's see if I can get there. Here is a GIF that is showing the actual parallax effect for Proxima Centauri. So named thusly because it is our nearest stellar neighbor. And you can see against the backdrop of much more distant objects, the baseline between Earth and New Horizons, which I actually can't remember what it is at the time of this these images. But you can actually very, very clearly see as you take images from widely separated positions that you watch as the much more nearby object, so Proxima Centauri in this case, shifts against this backdrop of.
That's pretty amazing.
Objects. This is super cool.
Yeah.
Again, this is like if you stuck your thumb out at arm's length in front of your face, and if you closed one eye, and then if you closed the other eye, but open that first eye. So you're changing which eye is closed and which eye is open. And you can see that even that kind of small baseline between your eyes, if you switch which one you're using, actually causes you to see your thumb appear in different places against the backdrop of your wall or whatever. Pretty cool stuff. This is a really neat way. There was a whole campaign in April to get a bunch of amateur astronomers to take data, and then you can do this kind of image blinking with the actual space-based data from the New Horizons spacecraft and see the parallax. Super tangible and really, really awesome. I like that one.
It reminds me of Wayne's World, when Wayne, played by Mike Myers, is like camera 1, camera 2, camera 1, camera 1.
Camera 1, camera 2. That's a
I use that in my demonstration of parallax in front of classes.
All right, next one is NASA partnered with SpaceX to launch US astronauts into space using American rockets for the first time since what year? We've got 2007, 2011, 2014, and 2015. What I should have done for this one is taken a poll to see how many people either watched it live or were able to watch it afterward.
Did you watch it?
Yeah, I did. There was a good, the nasa.gov.tv or nasa.tv, I can't remember what the URL is, but they had a great stream of it. What about, did the rest of you end up watching it?
Did you guys watch it, Arya, Paz?
I watched it after the fact, yeah.
I just like that the rockets come down and land back on the
the platform.
Pads out in the ocean. I think.
Though I'll notice I haven't watched every single one of those, but the like 3 or 4 that I've watched, the camera feed on the platform, on that pad, it's continuous, and it cuts out right before the rocket actually lands. You like see it coming down, and then like the half second before it lands, it cuts out, and then it turns back on, and you just see it there on the launch pad. I swear, it worked once. They saved the video, and that's what. Okay, so the answer is 2011. So this was under Obama's watch, actually. So I'm going to see if we can just take a few seconds and actually just watch.
I watched the second to last shuttle launch in 2011, third to last, second to last at Cape Canaveral. It was awesome. I highly recommend if you have the opportunity to go to Cape Canaveral and watch a launch. If you haven't, it's super. It's just a whole cool event.
Wow. I know there were a lot of astronomers that I was talking to that they were very nervous about watching it, myself included, about watching it live, just in case it did not go well. And so who wanted to wait until after the launch happened just to make sure. But I got to say, it was really thrilling to watch live and to think that it had been 9 years, almost a decade. And And I think, right, there are 2 astronauts and they're going to be on the ISS for, is it 6 months?
For a while, yeah.
For a while. Yeah. Ooh, cool stuff. Okay, we could keep, it's a pretty long video. You keep watching.
As I said, this is the first time.
All right. Next question.
Mm.
What do we got? So what potential dark matter candidate?
Whoa. Don't even get through reading this question and people are responding.
Yeah.
Boom.
Everyone's like, I know. What potential dark matter candidate was detected by the XENON experiment last week deep underground in an Italian mine? Do you like how I tried my British pronunciation? The XENON.
I prefer Gorgon here. I really like
Yeah.
Where did you come up with that answer?
That's crazy. I don't know why anybody's not picking Gorgon.
Picking Gorgon. Medusa, the Medusa dark matter candidate.
Yeah. Oh, I meant to write boson, not boron. So there's only really 2 options here.
Yeah, boron.
Yeah, I meant to write boson. More like moron, Henderson. Get with it. So graviton in the lead, running away with 3/4 of the vote. 3/4 of the votes. Good work, everybody. That is actually not the correct answer.
It's not the correct answer.
Correct answer is, we'll do elimination. It is not Gorgon.
It's not Gorgon.
Maybe that 1% watched Stranger Things recently. It is not the element boron. It is also not the element osmium. It is axion.
Axion. Yeah, so this is super exciting. It's unclear so far from the results. So the experiment is this XENON experiment, which is this large tank. Instead of being full of water, it's full of liquid xenon, which we all know, based on the periodic table, it's a noble gas. So it doesn't readily, it's pretty inert. It doesn't like to react with other things chemically. And it's this big tank of super pure xenon. And it sits down in this mine underneath a mountain in Italy, where a lot of these sorts of experiments are conducted, because when you're down in these subterranean chambers, you're blocked by much of the Earth, blocking a lot of the cosmic rays and other charged particles that are flying around space, and that would kind of present a noise source if you did this on the surface of the Earth. So you burrow down into the Earth, you do these experiments, whether for this or for neutrinos or dark matter experiments, where you're shielded from a lot of these charged particles, and you hope that you can detect some sort of interaction between a dark matter particle, assuming dark matter is in fact in particles, which we believe that it is, and whatever your vat is, whatever your fluid is, whatever your experiment is. And so there are a number of these using different methods to try and detect dark matter candidates, because we don't understand what the bulk of the mass in our universe is consisting of. That's why we call it dark matter. It's dark because we don't know what the heck is going on, but we see its presence through inferred properties of how it behaves dynamically and gravitationally with astrophysical objects like galaxies or clusters of galaxies, but it doesn't seem to interact, at least that we can tell, directly with the electromagnetic forces that we see through everything else. You can't shine light on it, that sort of thing. So anyway, so the signal that was detected through this experiment by looking for scintillation of potential interactions that might take place seems to suggest that there are axions present. Axions are a theoretically proposed particle from like 30 or 40 years ago, an extension of the standard model of particle physics that might exist. People proposed it as not as a dark matter candidate initially. It was proposed as a way of resolving a long-standing problem in particle physics, the CP violation problem, or well, CP symmetry in the strong force. I don't really want to get super deep in it, partially because I don't super well understand it either. I'm not a particle physicist, but the point is, this was proposed for other reasons. The particle is predicted to exist. No one's ever observed it, but it's a very low mass particle. It's like a billion or almost a trillion times less massive than an electron. It has no charge, it's neutral, like a neutron or a neutrino, and it has a weak interaction with normal other particles, like what we're made of, protons and electrons. So that's why they're looking for, well, something like that in these experiments. So the detection showed a 3 sigma detection, which normally for you to say I have a strong detection, it means that you have a 5 sigma detection, which means that it's something like the chance that it's not due to the thing that you're hypothesizing it's due to is like 1 in, I don't know, do you guys know what 5 sigma is? It's 1 in like a million or 1 in 10 million.
Yeah, I was going to look it up. I can't remember exactly.
But 3 sigma is like 1 in 10,000 that it's not correct. And so normally the standard is that something has to be a 5 sigma detection before you're really confident that you're correct.
So it's about 1 in 3.5 million.
Okay.
5 sigma.
So this hasn't reached that level of confidence, but it's suggestive that it was axions that were detected. But a couple of caveats: the axions would have been coming from the sun as opposed to the same stuff that's in dark matter everywhere, or not everywhere, but throughout the universe. And furthermore, it looks like the detection could have been caused if there was an unusual isotope called tritium, an isotope of hydrogen that was present there and could have decayed and given a similar signal to what they're seeing. But there are other experiments going on. One is a follow-up to this experiment that's a much larger tank that will be able to provide more constraints on this. And there are other experiments that detect axions in different ways that might be able to reveal whether or not this is real. But it's exciting because it's a new, it's suggestive that there's new stuff going on in particle physics that we've proposed, but we've never actually seen any real evidence of. So, and it could actually give us some clues as to what dark matter, which is the major constituent of the universe, is actually composed of, which is super exciting. So, I don't know. I thought this was really cool.
Yeah, this is really cool. It's an image of the actual experiment itself, and I knew it was large, that the volume of the experiment material was large, but it's something else to actually see an image with humans to scale, to get a sense of the actual.
Oh yeah, that's right. Because it's called xenon 1T because I think it's 1T because it's 1 ton of liquid xenon. And so yeah, the size of the fluid, fills the bulk of this container. It's pretty substantial. But they're doing the follow-on to this is xenon NT, which is meant to be something like 10 tons or 15. It's substantially larger and would provide better constraints.
That's cool. I mean, and I guess given that axions are so light, maybe that's how they make those like air puff Cheetos, because like those are pretty light too. And like I always wondered how they did that. It's like that's really cool.
We're gonna have to agree to disagree here. I don't know if that's what's responsible.
I don't know which way I'm falling down on that. I just think it's worth billions of research dollars.
Yeah.
All right, no, thank you. That's a cool. I did not know most of that. It's been a while since I've studied particle physics. All right, the final question, everybody's favorite. So longtime viewers of the program will know that we always have a Star Wars question. So here we go. In Star Wars, which industrial core world is the home planet of Han Solo and featured in the film Solo?
Yes.
Yeah.
Oh, Solo, a Star Wars story, I think is the full title.
A Star Wars story. That's my bad.
Star Wars story.
I hope everybody knew which movie I was referring to.
No ideas? I guess people are looking it up on Wikipedia.
Yeah. Everybody, we're empirically measuring the lag time of user Google.
Rather, not Wikipedia, Wookiepedia. That's where people.
Oh yeah. We're not going to give even partial credit for slightly misspelled answers, just to be, since everybody's bookmarking Wikipedia on their work phones. Or is that just me? Maybe that's just me. Oh, we got some cross universe here with Vulcan. I will note that Earth is not a cross universe answer because Star Wars are all documentaries because it happened a long time ago.
Okay.
And it says a galaxy far, far away, but they didn't mean that.
I see.
Lucas was just a very confused.
Address.
Oh yeah, somebody wrote Earth address.
I see. Okay. Whoa. Corellia.
Okay,
All
so
right.
a lot of people like Corellia with 2 L's.
Corellia.
Like
I actually liked the movie Solo. I didn't anticipate liking the movie Solo. I went into it with like the lowest of expectations, and I was like, oh, okay, that was pretty good actually. I mean, it wasn't about saving the universe from baddies, but
okay, look, I know that we don't have a lot of time left, and we shouldn't spend it on why that movie was a bad movie.
wait, what?
But
It's
if
bad?
anybody has any questions as to my thoughts, just write it in the chat, and I'll send you my 27-page treatise that I will rewrite tonight.
Really? You didn't like the film?
Okay, first off, what do you know about Han Solo going into Solo? The first time that you see Han Solo in the original trilogy is when he's cocky.
In the cantina.
He's in the Mos Eisley cantina.
Yeah.
He's seen some stuff. He has clearly done some stuff. He is in debt. He's on the run. He's being hunted. He is smarmy. And he's a bandit.
Yeah.
And all of Solo was him turning into a full-on Boy Scout, which I don't say pejoratively. They do very nice things. As an
I was a Boy Scout. How dare you?
I am also an Eagle Scout. And I just think that was the one chance to actually show like the darker, grimier side of the Star Wars universe, which they did a great job of in Rogue One with Cassian Andor. That's a good movie. That's a good movie.
Yeah,
Also,
Rogue One was excellent. Rogue One was excellent.
Solo.
I'm not saying that it wasn't, but so you think it was too Boy Scouty? You thought it was? You thought Solo was too like?
Yes.
Oh, jeez.
100,000%. All of the percents. I just think, let's talk. Okay, I don't want to give spoilers for Rogue One, but I think the statute has passed. When they're on the planet at the end of Rogue One and Blue Squadron is saving them, and you're like, wait a minute, there was no Blue Squadron in A New Hope. And then you're like, oh, there's only one way. And that's not to mention Cassian Andor, shooting his informant in one of the opening scenes.
Oh,
meanwhile,
the first
Han
time we meet Han Solo is when he shoots Greedo. Are you kidding
exactly.
me?
So how do you get from the Han Solo in Solo, a Star Wars story, to the Han Solo that you meet in the Mos Eisley Cantina? There is no. Okay, let's just go to the answer.
The answer is Corellia.
The answer is Corellia. And here, this is an actual. So I was Googling, looking on the NASA.gov website. This is an image taken using actual data of Corellia. You'll note land masses. You can see kind of telltale signs of humanoid civilizations. There's meteorological features. There's liquid, presumably water. This planet is known to be habitable. That's why it's been industrial, and it's one of the core planets in the system. This is not to be confused with Coruscant. They kind of sound similar. There's a hyper-industrial, pure city planet, which is actually the seat of the empire. I tried looking up the coordinates to take some data on Corellia, but Wikipedia I think was a little out of date. Couldn't find the RA deck.
Yeah, you need to give that to Tess. Tess can really give us the deets on.
Yeah, Tess. I hope it's in the continuous viewing zone. All right, that's I'm gonna stop sharing now. Thank you everybody for participating in the trivia. Feel free to share your thoughts. This is our second time doing the trivia in this format, so it is a little bit different, as evidenced by me having a little bit of a technical difficulty at the beginning. We kind of like it that it can be more interactive and show images and videos, but let us know what you think. If you like it, definitely let us know what you think. And if you didn't like it, I'm sure you've already let us know what you think.
Yeah, give us a big thumbs down if you're like, this sucks.
Yeah, you're like, and if you give us a thumbs down, We will only listen if you also say that Solo is not your favorite Star Wars.
Oh, jeez. Okay. All right. Someone in the comments has asked, Laura May, I believe, asked, can we do a poll on which of the last Star Wars was the best?
Oh, that is.
This could turn into a whole thing. This could turn into a whole thing.
You know what? Why don't we do that? Why don't we make that the Star Wars question for the next
next one, which is how do you rank the Star Wars? I mean, we can do the whole,
yeah,
the whole pantheon.
Yeah,
it's going to take some deep thinking here.
I'm not even going to include Solo because no one's going to choose it.
Oh, Halen, I'm going to fire you.
It's obviously 5, Rogue One, 4, 6, everything else.
No, what? No, you put 4 in front of 6.
Oh please,
Jedi's so good.
Bears have no business.
Don't worry about the Ewoks. The first act in Episode 6 is like the greatest act in the entirety of Star Wars.
Paz, what is your favorite Star Wars movie?
I will give the blasphemous answer that I don't actually like Star Wars.
That's okay. That's okay.
That's actually better than saying Solo.
It's better than saying Solo sucks.
Arya, what is your favorite Star Wars movie?
The 4.
Oh,
Okay.
4. Okay,
I like that. That's a
controversial.
dark horse.
Controversial. We should have done this today. This is good. This is real.
Oh. Well, it'll be first question of the trivia, and that'll be the second hour of the program.
Yeah. All right. Well, thank you everyone for attending. We'll continue to have these. I anticipate we'll probably continue to do live stream throughout the end of 2020. I don't anticipate going back to a bar in the next few months. We're not going to have any kind of vaccines before the new year, probably not for a considerable time after that. I don't want to go breathe all y'all's breaths. That's not good for me. That's not good for you. It's not good for anybody. So
If I breathe your breath, I might like Solo.
Oh, jeez. So we'll probably continue to do it this way. Our next Astronomy on Tap, the date we're doing it is, Arya referred to this, we're doing it July 20th, which is the launch date of Mars 2020, Perseverance, which is going to be exciting. It's probably going to be all about Mars because Mars is great and exciting. In the sister series to these Astronomy on Tap events, we have our public lectures at Caltech Astronomy. They're a little bit more formal. They don't have people drinking invisible beers. And so those consist of a 30-minute talk on some research topic given by somebody at Caltech, and then a Q&A session for 90 or so minutes after that by a number of different researchers, kind of like this, but without the beer and without the Star Wars discussion. So our next one of those will be July 10th, given by PhD student Kisha Day, who will be talking about invisible explosions, so supernovae that are buried deep within dust envelopes, so we can't see them in the optical, we can't see them in visible wavelengths, but using telescopes that are akin to night vision goggles to be able to actually see those and what it reveals about supernovae and what it reveals about the dynamic universe. So that will be July 10th. Astronomy on Tap will be July 20th on Mars stuff, and should be fun. So one of the astronomy lecture is already in our YouTube channel. You can already click like set reminder if you actually want to go. No pressure from me. And otherwise, check social media, check this YouTube channel for our other events. And all of our other events are recorded, so you can go back through our history and see other talks on a variety of different topics. But thank you very much to both of our speakers, Dr. Arya Udry from UNLV, Dr. Paz Beniamini from Caltech. This was awesome. And everything was great except for Kalen and his horrible statements about the Star Wars universe.
Unreal. Thank you, Arya. Thank you, Paz.
Thank
Cameron.
Thanks, that was fun.
Okay. Bye, guys.
Bye.